For the given vectors, u is 6, 2 in component form, and v is negative 3, 3. Find and draw u plus v, u minus v, and 3u plus 4v. If you would, take a second and find the component forms of a, b, and c first, and then we'll draw them all. So vector u plus vector v. Vector u is 6, 2. Vector v is negative 3, 3. So adding corresponding components, what would we get? 3, 5. Now we can check this. Vector u is 6, 2. That's vector u. Vector v is negative 3, 3. Is that okay? And when we were done, we got 3, 5. So notice, let me just try to copy this. What should appear to be the case is if you applied vector u and then from the terminal side of vector v, you applied vector v, hey, look at that! They should match right up. And that tells you if you did it right. So that's your parallelogram law, right? Or vice versa. If I copied vector u and started it at the end of vector v, it should go to that other point, the same point. Vector u minus vector v. Subtract corresponding components. Do not, unless you really like to lose points, do bad math. What's the x-coordinate? Y-coordinate? I shouldn't say x. I should say horizontal component and vertical component. So horizontal is 9, negative 1. So what this says is apply vector u and then take vector v in the opposite direction. So 9, negative 1. You can almost see it. So if we applied u, that's the blue one here. And then if we took v in the opposite direction, that's your negative v. Is that okay? And then now notice in part C, we have 2 scalar multiplications and an addition. What would 3 vector u look like? (18, 6) and 4 vector v. Adding them together and realizing there's not enough space on the board, hey, what are you going to do? Yep, you get 6 and 18. So if you extend it out u 3 times, extend it out v 4 times. This is called a linear combination. If you multiply and then add together or subtract, doesn't matter. So 6, 18. That looks good right there. I think I overshot that one. I can't believe it wrote that. That is still... Hooray!